In this video, we're going to be looking at a few other types of expansions that you need to be familiar with. In the last video, we looked at a reversible adiabatic expansion of an ideal gas. So here we're going to treat a few different scenarios, also assuming an ideal gas, different types of expansions that you need to be familiar with. So a very common type of question that you'll be asked is to solve for Q, W, and delta U for a specific type of expansion, right? So all of the key pieces of the first law of thermodynamics for a particular scenario. And we looked at one of those scenarios, the reversible adiabatic expansion. And there are a few other types that you should be familiar with. So the first one is an adiabatic irreversible expansion. So adiabatic irreversible. Right, so what's so special about an adiabatic irreversible expansion? Well, we know that since it's adiabatic, dq is going to be equal to 0. Right, so we know q is going to be 0 for an adiabatic case, right? So that means that the work is really the only contribution to the first law of thermodynamics. It's just going to be that du. Right, so if we think about the first law of thermodynamics, du is equal to dq plus dw. If dq is 0, then that means du is just equal to dw. So all we have to do is just solve for the work in order to solve for both du and dw. So obviously for any expansion, dw is going to be equal to negative p external dv. Now, this is where the fact that it's irreversible becomes very important. If the expansion is irreversible, then that means that we don't have an established mechanical equilibrium between the gas and the outside external pressure. So this external pressure is just going to be a constant applied external pressure to the system. So that means that when you're solving for W, right, when you're solving for the work, that guy can come out of the integral. And then you just integrate from V1 to V2. And then so your work is just going to be negative P external delta V. Right, so that gives you your work. And since du is equal to dw, delta U is just going to be equal to W. Right, so they're just going to be equal to the exact same thing. So this solves for Q, delta U, and W for an adiabatic irreversible case. Right, so the next process that you should be familiar with is an isothermal irreversible expansion. Right, so this one is isothermal irreversible. Right, okay, so an isothermal irreversible expansion. Okay, so with an isothermal irreversible expansion, right, we're still dealing with a gas expansion, so the work is going to be exactly the same as our adiabatic irreversible case. So let's go ahead and write that down. Right, so our work is going to be exactly the same as it was in this adiabatic irreversible case, right? Now, let's recall that for an ideal gas, right, our du is simply equal to Cv dt. Well, if our expansion is isothermal, that means dt is going to be equal to 0. And if that's true, then this whole term goes to 0. So that means du is just going to be equal to 0, which means that delta U, our total change in internal energy, is just going to be equal to 0, right? Because we've seen that in the case of an ideal gas, its internal energy is completely dependent on a temperature change. If there is no temperature change, then we have no change in internal energy. Okay, so now what consequence does delta U being 0 have on the first law of thermodynamics? Well, let's look at it. So we know that for the first law, delta U is equal to Q plus W, right? if we know that this whole thing is going to be equal to 0, then that means that Q is just going to be equal to negative W. So in this case, Q is going to be equal to P external delta V, right? Because that's what we got for our work. All we have to do is just change the sign, and that gives us Q in this case, right? So that's going to be for an isothermal irreversible expansion, right? So isothermal irreversible, the work is exactly the same as an adiabatic irreversible, but in this case, delta U is going to be 0 for an ideal gas. So Q is just equal to negative W in that case. Okay, cool. The last one that I want you guys to be familiar with is an isothermal reversible expansion. Isothermal reversible. So now in this case, since it's reversible, we do have to account for the fact that we have this mechanical equilibrium established. So for the work, that's going to be equal to negative, or the dW, I should say, it's going to be equal to negative P dV, right? Where we actually will have to use our state function for pressure, right? So if we want to get W, then we'll have to integrate, right, from V1 to V2 of P dV, right? For an ideal gas, we know what our expression is going to be. So we're going to have from V1 to V2, right? We can just plug in our nRT over V dV. We can pull out nRT and just end up with the final expression of nRT, negative nRT, ln V2 over V1, right? So that's going to be the work in the case of an isothermal reversible reversible expansion, right? Now, for this case, if it's isothermal, right? So just like we saw above in the isothermal irreversible case, delta U is also going to be 0 in this case for an isothermal reversible expansion, right? So delta U is going to be 0. So this same relationship between Q and W exists. So that means that Q, for this case, would just be nRT ln V2 over V1. Right, so that's going to be Q, W, and delta U for an isothermal reversible expansion. Okay, so those are the really 4 common types of expansions or compressions that you'll encounter in most of these problems in physical chemistry. Like I said, a very common type of question is to ask you to calculate U, W, and Q for a particular type of expansion. And potentially enthalpy as well. We're going to add on more state variables that you can calculate throughout these expansions, but just making sure that you're familiar with the differences between them is crucial. And as you can see, it really just boils down to looking at what the effect on the first law of thermodynamics is going to be. Okay, if it's adiabatic, that means Q is 0. That means that my delta U is going to be equal to W, right? So just looking at how your conditions affect the first law of thermodynamics is really half the battle in solving these types of problems.